z-score, you guys should have gotten 233. So eventually we're going to be using certain z-scores a lot. 95% confidence interval is the most often used one. That was the 1.96. 90% is 1645. 98% is 233. Ooh. So the more you do this stuff, the more you're going to remember these numbers. Don't freak out if you start doing that. Is it really cool with this? I mean, I told you these. What sucks is if you misidentify a number, put it in the wrong place. At the heart of this is the only thing you really have to calculate yourself for most of these problems. So otherwise it's just plug and shove. And I think the error you should get is 0.999. Almost 1 inch off. So then you end up basically going from 63.17 to 65.17. Now you don't have to calculate the error separately like this, but it's a good idea because a lot of times they ask you for the error directly. So then how do you write the conclusion? We are 98% confident that the interval 63.17 inches to 65.17 inches contains the true mean height of women in a certain city. And you're all like, there's a lot of words, man. It's math class. Sorry, just reading your mind. Too bad. This is stats class. Even math is not done at the numbers. But stats especially is not done at the numbers. So with a sample of 34, we get an error of almost an inch. So now for part B it says, how large of a sample would I need to cut that error down to just half an inch? So part B now. Do you see how that word within, that's a key word. They don't always use the word within, but if I see the word within, that's going to be the error. Within so much. Plus or minus so much. So my z-score is the same because it's still at 98% confidence. Standard deviation is the same. But now I want my error to be half an inch tall. Half an inch in height. I guess half an inch tall. I mean, hello. What do you get? And no matter what you round it up, so you don't have to figure out how to get that last fraction of a woman. That would be freaky. Oh. So does it make sense? 136 women give me half an inch error. Only 34 women give me an inch. That makes sense. I have to take a lot larger sample to get a much smaller error. Makes sense. All right. So the last part C. Let's see if we can do this real quick because it's the same work, just a different. One thing is different. Would it be larger or smaller than 90%? Would it be wider or narrower? Well, it would be smaller because I only have to go so far out to just catch 90%. I catch 8% less.
So it's based off the question pattern? It's based off the question?
Yes. This is all one ABC, so it's all based on the same thing. Blah, 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 blah. Why not create the 90% confidence? So the only thing that changes from this, it's going to be the exact same formula except what? Z-score now for 90%. Yes, 1.645. I don't know if any of you have noticed what they call the baby chart. See where it says confidence level? Those are the three most used ones, 90%, 95%, 99%. So 1.6 for 5. And then all the work's the same. So now you just got a new error. The error is going to be a little bit less because they don't have to be as certain anymore. 0.7? 0.706? Okay. 705? 3? Okay. And then you just subtract that, add that.
And 64.875.
That sounds all right. So then we are, did I ask you to do the whole thing there? No. Normally, though, you're going to want to do that. On a test or a quiz, I would try to be sure to say, write the conclusion, but you pretty much should always write your conclusion. How are we doing? You should always write your conclusion. All right, so last thing for today. I love you guys. Everybody, that poor clock, man. It's got so many eyes on it all the time. Last thing for today. How are we doing about this? This is kind of nice because it's nothing really new exactly. It's just a reorganization of all this old stuff. The new thing is kind of the wording of the conclusion. What I kind of like to do, section 8.2 introduces an entirely new distribution. So I like to kind of skip it for a minute, go to 8.3. So remember how we started here? Let me just go ahead and put a plus or minus in there because we know where we're going. Well, you know, we sort of started, we really make it quick. We started here, really, right? I don't know if you guys remember or not. We said, okay, we have it this way. Okay, now. I'm going to show you where this percentage confidence interval formula comes from. So if you don't entirely follow this derivation, it's not the end of the world. The minute I say that, certain people just kind of tune out. But please try to follow. Help me out. So in a binomial situation, oh shit. Because percentages are normally either you do or you don't. In fact, that's how we're going to look at these. Is this or it ain't this? So it's going to be a binomial. That's the one we have percentages, P and Q. What was the mean for a binomial, for an NPQ situation?
N times P.
Yes, N times P. And what was the standard deviation?
Square root of
N times Q.
Alright, normally that gets you started, gets you going. Alright. Now, here's what you're going to love this. This takes me back to somehow it takes me back to my fishing days. That ties in with the earlier thing. This is known to be a population percentage. I don't know if you've ever noticed that, but it's always like 11% of all Americans are left-handed, or 34% of all the people want to vote for this, or whatever. It's always been a population thing. What we're going to do, if we're wanting to know what percentage of people seem to want to vote for something, what do? We go out and we talk to a selection of people, or we call them up or something, right? So we're dealing with a sample, so I can't use P, because P by itself means the population percentage. Oh shit. So of course what we do is we use something called P hat. It's not me, you're a goofball, you probably made that up or something. No, I didn't. It's the actual P hat means sample percentage. Just like X has a bar over it, and that's like the sample mean. You can think of it like that. If it's wearing something, P is wearing a hat, or the P hat is the item of clothing you don't want to wear. So like, whatever makes it stick in your brain. That one was just for me, bro. So like if I told you, for a real quick example, if I poll 800 people and find that 727 of them are worried about the future, what percentage, what's P hat going to be? What would P hat be? We poll 800 people and find 727 of them are concerned about the future. What's P hat? What's the percentage concerned about the future?
9.
It can't be 9 point something, it's almost 100%. 90 something would make more sense. Yeah, so P hat would be 727 divided by 800. In fact, the formula they often give is X over N, because X is the number of successes, N is the sample size. Do you actually need that formula? You shouldn't. You should know how to make a percentage part divided by whole. Hello. It can't be bigger than 1. Alright, now watch. So what we did earlier was we said we can get this, but what's that going to be? Now let me see if you guys follow this. If the population mean is N times the population percentage, the sample mean is N times the sample percentage. It's crazy. We still got plus or minus. We still got Z. Those don't change. Now this was this, right? Is that cool? And let's see what. Oh, yeah, that's perfect. So right here, I'm going to put this, but I'm going to put hats in there because now I'm going to use the only thing I know, which is the sample percentages. And now, believe it or not, here's the weird part. Hopefully this isn't that big of a deal. I got to use little hats because it's not a population I got. I'm only going to talk about a sample of people or look at a sample or whatever. So I got to use the little hats in there. Otherwise, it was just a direct translation, right? Using the formulas that we know from before. Now, here's the part where it takes a little bit of understanding. I'm trying to capture mu, right? So I'm trying to capture mu is roughly this. It's somewhere in there. And mu is NP. So NP is roughly this. But I want my confidence interval to be, like 44% plus or minus 4%. I want my confidence interval to only be percentages. I just want P hat here. I don't want this stupid N. Stupid N. So what I do is I divide everything by N. So I get P hat plus or minus. Here's the next algebraic consideration. Can I just cancel those?
No.
Hell no, because one's in a radical and one ain't. How can I rectify that?
Multiply by square root of square.
What's the square root of what equals n?
N squared.
So I can rewrite that as the square root of n squared. I didn't change anything. Isn't that just equal to n? I love to look at it. Some of you guys are like, whatever math people, shit. But, please do God. 5 is equal to the square root of 5 squared, 25. Holy shit. So n is equal to the square root of n squared. End of story. There's a nice little short story. Right? Nothing major. Well, some of you guys looked at me like, really? What the hell? Not a big deal. Why did I do that weird shit? So that they both have a square root, so I can now cancel an n, right? Just trying to make this formula look a little better. So now I get plus or minus z square root of p hat, q hat over n. That is the formula for a confidence interval for percentages.
So we don't have to go through all that.
No, again, this is the derivation of where the formula comes from. So if you didn't quite follow or really never want to think about what I just said with all this, you don't really have to. I'm not going to let you escape the class without going through that though, right? How would I use this the same way? If I want to be 98% confident, guess what I put here? 2.33, right? We figured that out. So that can't change. Z-scores don't change what they contain. They always contain the same amount. They're going to have to tell me this stuff, or give me the way to figure out this stuff, which means they have to tell me how many people, and I've already got that. I mean, it's not going to be that bad. In fact, right here, I could do this. What did somebody get from p hat here? 0.9?
906.
906? What's q hat then? No matter what they're wearing, what's p plus q? You can do it. I know you can. What's probability of success plus probability of failure has to be 1. Thank you. Even if they're wearing hats. Right? So what's q hat going to be?
0.90.
What is it? Sorry?
0.909.
Oh, the p hat? 0.909?
Yeah. Yeah.
Okay. So I guess so what's q hat going to be?
109.
So 091. So that together they are 1. Just do 1 minus this, right? Same thing we've done before.
0.09.
Yep. And then, so you plug that in there. You plug these two in there. You plug 800, that's in. You plug that in there. And if I wanted 98% confidence, you put 2.33 there. It's kind of crazy. It's just a plug and chug thing where, again, the most weird thing probably is going to be figuring out what the z-score is. It's the same idea, though. I start here and I go out so many steps. And so I'm going to be that confident that I caught the real thing because I just caught that percentage of stuff. All right, that's enough. The faces are easier to read, but that's because they become more annoying. But